Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is Sinusoidal Steady State Analysis from Unit 3 Sinusoidal Steady State Analysis of Electric Circuit Analysis. On completion, the students will be able to understand the importance of sinusoidal steady state analysis and represent the voltage current relation for inductance and capacitance. Sinusoidal steady state analysis. Sinusoidal steady state analysis, which is also known as AC analysis, is a method used to analyze linear circuits driven by sinusoidal sources, that is voltage or current sources in a steady state condition. Sinusoidal source. A sinusoidal input can be written as V of t is equal to Vm cos omega t plus pi, where Vm is the amplitude, omega is angular frequency in radian per second, and pi is the phase angle. This sinusoidal steady state analysis can be used to analyze linear circuits driven by sinusoidal sources, and it focuses on steady state response after the decay of transients and converts time domain circuits into phasor, that is frequency domain. Phasor representation. To simplify the analysis, we can convert the time domain sinusoids to phasor or frequency domains, where V of t is equal to Vm cos omega t plus pi is written as Vm phase of pi. This transformation allows to use complex algebra instead of differential equations. Voltage current relation for an inductor. The voltage current relationship for an inductor in an electric circuit is described by the following equation, where V of t is given as L di by dt, where V of t is the instantaneous voltage across the inductor at a time t, L is the inductance of the inductor, I of t is the instantaneous current flowing through the inductor. This equation signifies that the voltage across an inductor is proportional to the rate of change of current with respect to time. And V can be given as J omega L into I. Then voltage leads the current by 90 degree. It can be written as V is equal to omega L Im phase of theta I plus 90 degree. Voltage current relationship for a capacitor. The voltage current relationship for a capacitor in an electrical circuit is given by the following equation, where the current I of t is given as C into dV by dV of t by dt. Then the voltage equation V can be given as 1 by J omega C into I, where C is the capacitance in farads. I of t is the instantaneous current flowing through the capacitor at time t. C is the capacitance, and V of t is the instantaneous voltage across the capacitor. This equation describes that the current through a capacitor is proportional to the rate of change of voltage with respect to time t. The voltage across the terminals of a capacitor lags by the current by 90 degree, and it is given as V is equal to Im by omega C, phase angle of theta I minus 90 degree. Impedance. Impedance we can obtain by replacing the reactive components as given here. As resistor, it is represented as ZR, which is equal to R, inductor ZL, which is equal to J omega L, and capacitor can be given as ZC, which is 1 by J omega C. Example problem for RL circuit analysis. V S of t is given as 10 cos 1000 t, and R is 1 ohm and L is 1 millihenry. While converting the source to a phasor value, we are getting the voltage Vs is equal to 10 angle 0, and its impedance Z is given as 1 plus J omega L, as R is 1 and L is also 1. Omega is L is given as 1 into 10 to the power minus 3, and omega is 1000, and substituting we are getting the Z value as 1 plus J1, and the current is given as V by R or V by Z, which is 10 angle 0 divided by 1 plus J1, and the value is obtained in phasor form as 7.07 angle minus 45 degree. We can convert this phasor result back to time domain. It is obtained as I of t is equal to 7.07 cos 1000 t minus 45 degree. Quiz questions on sinusoidal steady state analysis. Explain with an example how do you convert time domain to phasor and phasor to time domain. Write down the equations representing the voltage current relationship for a capacitor and an inductor. Thank you.